Hello, my name is Artem Sorokin, and I'm presenting our paper, QRAC Long Context Multi-Step Retrieval via Value-Based Embedder Training. So long context is still a problem for large language models, as quadratic attention makes training and inference on long context prohibitively expensive. There is a lot of different approaches to handling long context that include recurrent transformers, state space models, agents that build knowledge graphs, and a lot of different multi-step RAG methods. The most popular recent approach to multi-step RAG methods is to train an LLM to use RAG as a tool. But it's quite expensive. We didn't have resources to do something like this, so we decided to create something cheaper. Our main idea is the following. Instead of training an LLM, we train the embedder itself. And in this way, we don't need to generate intermediate search queries in text and then embed them and then actually search them. We can generate search queries directly in the embedding space. We can, to do this, we can formulate multi-step retrieval process as a Markov decision process. So in this MDP, a state is a query and all information that we already found. The action space consists of chunks that are still available for retrieval. We use sparse reward function that returns 1 when we found all the supporting chunks and returns 0 otherwise. The main thing here is that we train embedders so their inner product between state embedding and action embedding approximate state action value function. In this way, inner product between embeddings that usually approximate semantic similarity. In our case, it approximates utility. How useful is chunk A for our current state, for our initial query, given that all information that we already know. To encourage exploration, we use max entropy RL formulation for value functions. And given the Q function, we can compute our policy as a softmax over Q function values. Sometimes you don't run QRAC on disjointed documents like wiki. Sometimes you deal with a single narrative document, for example, a book, a fiction, something like this. And in this case, content of the chunk is not only thing that matters. Sometimes you also need to reason and to think about where this information lies. In the beginning of the document, in the end of the document, or between two events that are valuable to you. So to account for these cases, we create relative positional encodings. Basically, the main thing you need to understand about relative positional encodings is that it modifies chunk embeddings so that a model can reason about where this chunk lies in the document and how position of this chunk relates to all the previous retrieved chunks and their positions. We tested our method on several benchmarks, mainly long context benchmarks and open domain question answering benchmarks. We tested against many like recurrent transformers, other RAG and multi-step RAG methods, and even graph building methods. We get results, we get state-of-the-art results on Babylon, beating basically all recurrent transformers that we can find. And we have competitive results on open domain question answering benchmarks. But the main advantage our is the following. For example, you have a strong multi-step RAG baseline like Searcher 1, RAG RL, but these baselines need 8 GPUs to fine-tune because they fine-tuning an LLM. And we only fine-tuning an embedder, which is much, much smaller. So to get the similar result, we fine-tune, we need only 1 GPU instead of 8. So this makes, I don't know, research and practice more accessible for people. And I don't know, that's basically all.